My name is StephCacioppo. As John elegantly described in his talk, the Chicago Electrical Neuroimaging Analytics provides several advantages over prior methods for segmenting event-related brain potentials into brain microstates. Compared to existing methods such as the K-cluster analysis, the current microstate approach offers two main advantages. The first one is the automatic detection of two types of brain states. Using the baseline, SINA can identify functional brain states as well as transition states. This analytical suite improves the segmentation of time-variant data by providing moment-by-moment information about the entire spatial temporal dynamics of complex data set. This solves the issue of incomplete temporal state detection. A second advantage of SINA is the data-driven brain microstate identification. With SINA, we no longer need to determine a priori the number of clusters one should observe in the results. This analytical suite of tools thus improves hypothesis testing over prior microsegmentation techniques by eliminating confirmatory bias that results from an investigator specifying a priori how many microstates should be observed. This solves a critical issue in the field, the issue of sporadic and unreliable temporal state detection. In my talk today, I will present three empirical studies that I hope will illustrate the utility of SINA as a robust, accurate, and data-driven temporal segmentation of human electrical brain activity. Because of time limitation, I will focus in my talk on the functional brain states rather than transition states. As John described in his talk, the use of SINA is pretty straightforward. As you can see here on this slide, SINA is an open source platform implemented in Brainstorm as a plugin. SINA is freely available for academic use upon request at hpen@uchicago.edu. As you can see on this slide, after specifying the duration of your baseline, as well as a few parameters that we described in our tutorial, SINA will provide you with information about onset, offset, standard deviation of your microstates, and global field power. And from this SINA analysis, you will obtain a series of specific brain microstates that are statistically significant and explain your brain activity evoked by your stimulus. What about more complex experimental design, such as a 2x2 mixed model factorial design with word type, social, non-social, and word valence, positive, negative, as within subject factors, and loneliness, for instance, high and low, as a between subjects factor. The evolutionary model of the effects of perceived isolation on the brain, as well as a growing body of evidence, suggests that loneliness promotes automatic self-preservation, including an increased implicit hypervigilance for social threat that should be observed in the early stages of information processing. However, this hypothesis has not been tested previously in electrical neuroimaging studies. To address this question, we therefore used high-density EEG, SINA, and a social stroop interference task to test the hypothesis that implicit attention to negative social, in contrast to non-social words in the stroop task, differs between individuals high versus low in loneliness. We investigated this question in 70 individuals, 30 of whom were low in loneliness and 38 of whom were high in loneliness. During the task, the subjects were instructed to indicate as quickly and as accurately as possible the color of the ink of each centrally presented strings of letters by pressing one of 4 keys with the 4 fingers from their right dominant hand. In terms of SINA analysis, a priori orthogonal contrasts were conducted to determine differences between lonely and non-lonely individuals in the event-related microstates elicited by social and non-social negative stimuli. A parallel set of orthogonal contrasts were conducted for positive stimuli. Because of time limitation today, I will focus on the negative stimuli. The work type by loneliness interaction test revealed a significant difference for the period ranging from 280 milliseconds to 960 milliseconds, and again from 976 milliseconds to the end of the recording period, which was 1 second. To better understand this interaction, the ERP in the 128-dimensional sensor space was next investigated by performing simple main-effect tests within lonely participants and within non-lonely participants. The simple effect tests were performed within subjects to ensure the ERP waveform as a function of word type was investigated within the same set of brains and across average waveforms calculated from the same number of trials. The first effect test focused on the contrast between negative social and negative non-social in subjects low in loneliness. As expected, the results indicated that the first 5 microstates, from 92 milliseconds to 488 milliseconds post-stimulus onset, elicited by the Stroop task, were the same for negative social and negative non-social words. After 490 milliseconds post-stimulus onset, 3 additional discrete event-related microstates followed in both the negative social word condition and the negative non-social word condition. Interestingly, the first of these latter evoked microstates was evoked at a similar point in time in the negative social and non-social word conditions, but the state ended 50 milliseconds later in the negative social word condition, whereas this microstate lasted much longer, 394 milliseconds in the negative non-social word condition. These results emphasize the importance of timing in information processing. Finally, distributed cortical source estimations were performed to investigate the brain generators of each one of these microstates. Although SINA may serve as a better basis for source localization estimates, in part because it differentiates stable brain microstates from transitions between states, it is worth noting that the inferences drawn from the source analysis here are for purposes of hypothesis generation only, not for hypothesis testing. The results are illustrated in the bottom of the slide. The present study provides the first evidence that negative social stimuli are differentiated from negative non-social stimuli more quickly in the lonely brains than in the non-lonely brains. Given the timing of this differentiation in the brain and the fact that participants were performing a Stroop task, these results also suggest that these differences reflect implicit rather than explicit attentional differences between lonely and non-lonely individuals. Together, these results are in accord with the evolutionary model of loneliness. That said, the evolutionary model of loneliness didn't specify that these automatic processes would be specific to words. These automatic processes should be also observed for different types of stimuli, such as images. To address this question, we again used high-density EEG, SINA, and a social threat interference task to test the hypothesis that implicit attention to negative social, in contrast to non-social images in the task, differs between individuals high versus low in loneliness. We investigated this question in 19 individuals. Using the mean loneliness score of 42.26, 10 of the participants were grouped as lonely, while 9 of them were grouped as non-lonely. As in task 2, the experimental design of this third task was a 2x2 mixed model factorial design with image type, social, non-social, and image nature, neutral and threat as within subjects factors, and loneliness, high and low, as a between subjects factor. The participants were instructed to gaze at the center of the screen and were asked to view each picture. They made a categorical judgment regarding the valence of each image during the response slide. In terms of SINA analysis, a priori orthogonal contrasts were conducted again to determine differences between lonely and non-lonely individuals in the event-related microstates elicited by social and non-social threat images. As expected, the 2x2 interaction contrast with level of loneliness and type of stimulus reveals significant differences in the evoked brain response. These differences were observed for different periods of time, as you can see on the slide. To better understand this interaction, the ERP in the 128-dimensional sensor space was next investigated by performing simple man-effect tests within lonely participants and within non-lonely participants. As expected by the evolutionary model of loneliness, the first simple effect test contrasting the effects of social threat and non-social threat stimuli in lonely individuals revealed the difference between social threat and non-social threat in the very early stages of information processing. Indeed, after an initial common brain microstates, within the first 112 milliseconds, lonely participants showed 5 additional discrete event-related microstates in response to the social threat stimuli, and 7 additional event-related microstates in response to non-social threat stimuli. The second simple effect test contrasted the effects of social threat and non-social threat stimuli in non-lonely participants. As suggested by the interaction test, the discrete brain microstates evoked in non-lonely participants by social and non-social stimuli were quite different than those observed in lonely individuals. Specifically, in contrast to the lonely participants who only showed 1 common brain microstate in response to both a social and non-social threat, non-lonely individuals showed 5 initial common brain microstates in response to both a social and non-social threat stimuli. The remaining evoked microstates differed as a function of stimulus type, with 4 microstates elicited in the social threat stimulus condition and 4 microstates elicited in the non-social threat stimulus condition. Finally, brain source estimations of these microstates reveal somewhat similar generators for both social and non-social stimuli within brain networks associated with emotional processing, attention, and perspective taking, with the exception that non-social stimuli activated brain areas more associated with biological motion, and social stimuli activated brain areas more associated with social cognition. Together, these results suggest that the elicited brain microstates in lonely participants differed early for social and non-social threats, with fewer discrete microstates elicited by social than non-social threats, whereas the simple man effect test within the non-lonely participants reflected a number of discrete brain microstates that were common across both social and non-social threats. Together, these findings provide more support for the notion that the implicit vigilance for social threat is higher in lonely than non-lonely individuals. In sum, the current research provides additional information on how loneliness impacts the processing of threatening stimuli. The estimated regions of brain activation need to be validated in statistically well-powered fMRI studies, but the present results suggest there were a greater number of evoked brain microstates and a much richer spatial and temporal sequence of regional brain activation than hypothesized and than observed in prior research. This better understanding will increase further as scientists refine their recording and analytical techniques. With the use of CNA, we hope a better quantitative procedure for identifying stable event-related brain microstates has been introduced here and may serve as a better basis for source localization estimates. Through a series of simulations and empirical studies, we demonstrated that CNA helps identify not only where the underlying neural correlates are for a task, but how these components are parsed across time into specific operating brain microstates whose computations together define a particular processing operation. Thank you for your attention.